This meeting is being recorded.
Okay, now, welcome everybody to the June meeting of the Seattle Robotics Society. Glad you guys could be here. I am coming to you. Let's see here, let's get that out of the way. It'll take it, I'm sure it'll take it a moment here to come up on your, okay. There's that. Oops. Let me see. Oh, wait a second. Wrong slideshow. Sorry about that. Let me get to the right one here. Okay, there we go. Stop it. There we go. So, I am coming to you from Salt Lake City, Utah. My wife and daughters and I are, our daughter and I are attending a conference here at the Salt Palace in downtown. Is that it? Richard, have you ever been to anything at this place? I'm seeing
No, I left Utah just before the tornado ripped through that building. And I haven't been back to Utah since, and I'm okay with that. Yeah.
So they're my wife and my daughter and a friend are all at this place at a conference, big conference that's going on there. This is, gigantic place. It's like, I think it's almost 2/3 of a million square feet. I mean, it's like 600,000 square feet. The place is just gigantic. You spend way too much time. Oh, come on. Why does it keep doing? Okay, I'm going to shut that off. This thing keeps clicking over to the other presentation. Okay, here we go. Oops. No, sorry about that. Let me see. Maybe it does it. There we go. There we go. There's another view. You can actually kind of see the whole place. I mean, it covers, and Utah has, Salt Lake City has these enormous blocks. They're like, I don't know, whatever, the distance between streets is huge. I don't remember, it's probably some big, I don't even think about what the number is, but it's huge. It's probably twice as big, if not larger, than a typical city block in most other places. And this place covers like 4 of those, so it's enormous. And I spend way too much time just wandering aimlessly around this place. So anyway, that's I'm actually heading over there to join them for lunch later. So and I'm on mountain time here, so it's actually 11 a.m. or 11-ish a.m. my time. So I get to sleep in on these when I get to do these meetings from these other time zones. It's awesome. So here's the agenda that we'll be following for the most part today. And as you are aware, we are recording the meeting, and it will be posted to our webpage and YouTube channel, SRS Clips and More, later, possibly sometime this week. We're here for a few more days, and then we're going to Portland, and then we're finally getting home. So I'll see when I get around to doing it. But just a general housekeeping here. If you are not talking, please mute your microphones so that we don't interrupt people that are. And if you have stuff to contribute, links, notes, whatever, shoot them into the Zoom chat. And it's also a good place to ask questions. Oh yeah, I think you're right. The blocks are 660 feet on each side. Okay, yeah. I know it was something like that. And the center of Salt Lake City is like right across the street from that place. The Temple Square is like the 00 coordinate 00 in the middle of the city. Yeah. So. So, yeah, I think you're right. The blocks are 660 feet on each side. Okay, yeah, I know it was something like that. And the center of Salt Lake City is like right across the street from that place. The Temple Square is like the 00 coordinate 00 in the middle of the city. Yeah. So. fact, I was walking back to my car, and there was like this elderly couple were wandering around going, do you know where Temple Square is? You know, and so I figured a couple of Mormon pilgrims there, you know, trying to find Temple Square. So yeah, and I had to pull out my phone because I'm not a native there, so I didn't really know, but I knew it was close. And yeah, sure enough, it's just, I said, well, it's just on the other side of this monstrous building, you know. So I hope they made it.
Finding temples are easy. You just count down.
Yeah. The thing is that it's just everything is so big and so far apart, you know, you just have to keep walking. It's like, well, yeah, if you go that way about a block, which is like a quarter of a mile, and then you go that way, and then so yeah. So anyway, so post information to the chat, and then that will be included in the post that I put up after the meetings. I have not heard back from Kevin Ross regarding the new facility. I pinged him a couple of times via email, so I don't know if he's really busy or out of town or what. So I'll keep pestering him. You know, so we kind of hope that maybe this month or maybe next month we could actually start in-person meetings again, but don't know. So let's see. Yeah, the website is. Most of you have probably seen it. Go ahead and, you know, send me any feedback at the email listed on the page there. If you got any, you know, anything that's missing or you think ought to be there. Pretty much, I think everything is available that used to be available, and then of course the new format in WordPress instead of in the old fixed HTML, except for the old website. Let's see. Yeah, so we're planning to continue online meetings after we start meeting in person again. So that will hopefully you know, allow those of you who may not be able to or want to make the trek from where you live to where we do the meetings. You'll be able to join us. So let's see here. And let's see, and I think events coming. There's the National Drive Electric Week, the spring, what would you call it? The spring sessions are done, but then there's more coming in the fall. So in I believe it's in late September, early October, or something in September. There's more Drive Electric Weeks events happening. So. If that's anything you're interested in. Keep soliciting presenters. I will show you that who I've lined up so far here, and it's been pretty cool. So, but just send them to the Sail Robotics Gmail, and I'll reach out to the folks and see if we can get them to come online and chat with us, or come visit us if we get to that. So here's the lineup. So as you can see, we have people all the way through to the end of the year now. So I'm encouraged by that, and so we're now into 2023 for our open spots. So I will continue to try to see if I can sort of start to fill that in, but I won't work quite as hard now, having things already. No, James, you talked about it a couple of times, and you said you were going to do it, and so you're actually I think you had volunteered it to fill in a spot that I thought I had, and you did something else in that spot, as I recall. I think if you go back and look at the past meetings, you'll see what it was. So. And you sent me the presentation, so I had a chance to kind of look at it, but I don't think that you've done it for us yet. I don't know if there's anybody else out there that can confirm. It could be a meeting that I wasn't able to attend, but I don't think that you've presented yet on that topic.
I'm glad that you remember what I've done better than I do.
Yeah. Yeah, that was oh yeah, okay. So I'm planning, let's see, I'm going to back up here for just a second. So you see in December, there is the facilitated discussion on telemedicine, and RPM is remote patient monitoring. So that's the topic number 1 here on the open discussion lists. And well, actually, it's related to that, and I kind of expect that we'll probably talk about number 1 in that discussion, because it's kind of all part of the, you know, how technology and healthcare is you know, evolving. So so anyway, planning to do that at the end of the year, and we'll see where we see what kind of fun we have with that discussion. So later. Let's see, I was just, I don't know if anybody has noticed whether our presenter has joined us yet. I'm just going to do a quick scan through who's online with us here. I do not see him yet, so I'm hopeful that we will see him soon. No, not seeing him yet. So, anyway, yeah, and I saw that you got some good links there for building these things, and so hopefully this will be an interesting presentation for y'all. So I'm looking forward to it, and it's should be fun. Let's see. Oops. Okay. I don't think. I probably don't have anybody. I don't think I didn't see Lloyd or Donna on the call here, so I'll see if I can kind of summarize. So oh, that's funny. I wonder why. Oh, okay. So as you're probably aware, we're not going to have an in-person event this year, mainly because the Seattle Center is not committing. You know, it was not able to commit several months ago when we kind of need to lock this thing in, and they were still kind of, you know, had their concerns about whatever, and so you know, we have to lock this thing in probably at least 9 months before we want to do it, in order to be able to get everything done that is required to actually put the event on. So we are planning to do another virtual, let's see here. We're going to do another virtual event on August 27th, noon to 3 p.m. Pacific time. And so there are 4 presenters. I think, yeah, okay, so I believe there's four presenters. We could do as many as 6. So if that's something that you are interested in, if you have something that you'd like to present there, go jump over to the Robothon webpage, robothon.org, and you can sign up for that. And we would like to have some backups, and just in case people have to drop out. So even if we get our full quota, we'll probably want to have a couple of extras to just ensure that we have a full lineup on the day. So, and you can go to the SRS clips and more, and you can check out the YouTube videos of past events to get an idea of what those things are. But you know, 20 to 25 minute presentation on topic of your choice, project, demonstration of stuff you're working on. You know, it's pretty broad, probably along the lines of what our monthly presentations look like, but shortened to fit within the 20 to 25 minute window. So it's always an option to do. You could certainly do a monthly presentation or a month presentation for us at some future meeting too, and we're always more than happy to have that. We even if you've done a presentation on one of these, you're welcome to do one at a meeting as well. So anyway, just something to keep in mind. The practice session for the SRS PopCan Challenge happened, let's see, last month. I think it was last month, either last month or in late April, up at the Snowco Makerspace up by Painfield in Everett. And so the PopCan Challenge contest itself is scheduled for October 1st from 10 a.m. to 2 p.m. Pacific time. at the same location, and it will also be available online. So when they do it, they'll avail a Zoom link that you can use if you can't make it up there. It is a bit of a drive if you're not a North Ender, but anyway, something to keep in mind. And of course, obviously, they would love to have you come up there and join the spectating crowd. So, and so let's see. That looks. Okay, that looks like a repeat of a slide I already showed you guys. I'm not sure how that happened. Oops. Oh, I see. Sorry. It helps if I put my finger on the down arrow instead of the up arrow, you know, so sorry about that. We will go ahead and continue with post-meeting robotics stuff. So, you know, if you got things you want to continue to chat about, there's obviously during the round the room, you're more than welcome to bring up topics as well. There's nothing wrong with that. So, but after the meeting, we'll continue. We will probably we'll stop recording at the end of the official end of the meeting, and then after the presentation, and then we can just kind of continue hanging out and talking robots and whatever. Humidity is very low here, much lower than I'm used to, so I'm finding myself like I got to drink a lot. Yeah, and we were warned, especially if you spend a lot of time outdoors here, to drink plenty of water, a lot more water even than you normally would, just because you will dehydrate without even realizing it. So, yeah, I can definitely feel it in my throat. Okay, so that's enough of me blathering on here. So, has anybody got anything in particular they would like to share this month? I would hope that somebody has got an update for us, perhaps, or something, just some interesting thing, or a question, or a comment.
There's nothing about my robots, but I posted a couple of cool links in the chat. Stuff that I've come across over the course of the past month that I thought was pretty cool. There's a really interesting path-solving system on GitHub there. Anybody who's into path-solving robots should take a look at that. And then the other one is just a fun YouTube video. I don't know if you guys have seen that, but it's a 3D printer that prints a robot, which it then moves. So the 3D printer carriage causes this new robot to move in a way that actually builds a sandwich. I just think it's kind of hilarious. I mean, 3D printers are robots, right? So.
Well, you want to try sharing that? See if you can put that on.
Oh, it's in the chat. The link there.
Okay. Well, if you would like me to try, I can. Let me see what I can do here.
I figured something. I don't know if you want to take up time on it. You could also just, you know, have people look at it at their leisure. I just figured I should.
Well, you know, I mean, unless somebody else has something that they're just dying to share. I mean, this is what this part of the meeting is for. So, okay, let me get.
If you're looking for something for me to share, let me share this one really quick because it is absolutely hilarious to me.
Go ahead.
This is the world's simplest robot for turning a can over on a production line. That's hilarious. Like, if they had come to me and said, "We need you to build something that turns these cans over," I would have been programming a $5,000 robotic arm. I would have done, all kinds of research to figure out how to do it. And this guy takes 2 dirty rags and ties them around all of them, and it flips the cans over perfectly.
You gotta love just simple, basic ingenuity. I mean, somebody just, I mean, that is brilliant, you know, to come up with just a ridiculously simple solution to this problem. And of course, you know, what did it cost? You know, 10 cents or something. I mean,
yeah, in the old days, we used to call that value engineering.
Yeah, right.
That's right.
But
I think the only development time in that is like figuring out at what height to put the rags and how tightly to share them and all of that kind of stuff.
I think there might be more to it than that. Knocking the can over was the easy part. Getting it to stand back up again is where all the engineering came in.
Yeah.
Yeah, there was. I'm sure that there was a detailed analysis of tensile strength of the fabric versus the mass of the can and a geometric analysis. Just imagine the 3D modeling and simulations that had to be done before they worked out exactly the right dirty rag to tie across that.
Well, if you look at the second dirty rag, it's not just functioning as a rope across there. It dangles down to add extra weight to it so that it could catch the end and bring it back up again. You really got to give that engineer a lot of credit.
Yeah.
I think you're right. I think you're absolutely right.
And Steve, I can give a little update.
Okay, sure.
So if you look in my other window or frame, whatever you want to call it, you can see Gidget and Gidget's arm there. I'm almost to the point where I can command it to go to a specific XYZ location. Hoped I would be there by now to show you that, but it's just not quite working. What I did get working though was the there is a microcontroller on a board behind the wrist that controls the solenoid, senses the is hooked up to the Hall sensor for sensing the homing location. There's also a board inside of the gripper that is hooked up to the distance sensor and controls the servo there. Had a little bit of, they're both on a one-wire bus. Had a little bit of an issue there that I recently worked out. And so now I have things like the ability to tell the controller to home the gripper. So it's rotating it around until it gets to the Hall sensor there. I can tell the gripper to open and close over the one wire, and I can tell the wrist to release the pin, the locking pin, so that it can change tools. And then of course some of the motions that it's been able to do up to this point. But like I said, I'm almost to the point where I can give it an XYZ and have it go there. So progress, albeit slow progress.
Well, you take what you can get, right?
That's right. You'll notice you'll notice on the sides there that there's some white tape with some lines drawn. Prior to returning to the code for controlling all of this, I had always in my head, here, let me put it all the way in there. You may not be able to see it well, but so the arm is folded up right now. And I had always imagined that was 180 degrees. And when those two arm segments were aligned with each other, just a second. When those two arm segments were aligned with each other, that was 180. But because there is this little jog in the arm, that little jog is there so that it can fold flat. That little jog in the arm, having these two segments aligned does not line up the joints. So I had to put the tape and the lines on there because I was kind of going through these mental gymnastics to remind myself, oh, no. 180 looks like this, not like that. So that became really apparent when I started updating the control code for the driver and for the controller boards.
Yeah, kinematics and geometry are always fun. I'm curious, what is that tube with the yellow end and the lightning symbol on it?
That's the bumper.
Ah, okay, I see. Nice. And was there a reason for the lightning symbol, or did it just happen to be there?
It's got a lightning symbol on this end and a yield kind of warning symbol on the other. It's just there to tickle any kids that might notice it.
Like me.
Yeah.
It's great progress, Greg. Looks great.
Yeah.
And I'm pleased to report that let's close that it has no problem holding up the can. Let's see, if I were to say joint, shoulder, whoops, just a second. Where is it now? It's currently at 90 degrees. So I go joint, shoulder, let's say 120, and go. Yeah,
nice.
So it's able to. What happens if I tell it to park with the can on there? I've never done this.
Cool.
Yeah, there we go.
Demo.
Now, I did realize just the other day, the first time I put the arm in there, put the gripper on the end, if I recall correctly, for the Pup Can Challenge, the maximum, it has to fit into a 2-foot by 2-foot box. And I realized that with the hand sticking out there, it doesn't fit into that box. So I think its starting location or starting configuration is going to be something like that, which puts that behind the bumper, and bumper to tail is, I think, about 22 inches.
Greg, can I ask, on the wrist segment there's a clear piece of plastic sticking down. Am I right in assuming that is a height gauge to allow you to align the gripper at the proper point on the can relative to the height of the table?
That is incorrect.
So what is the of that piece of plastic?
That little piece of plastic, that is the door opening. For opening the door on the mini fridge.
Oh, okay. So you can hook it and then pull with
that. It will rotate the hand like that, slide down the side of the mini fridge until that drops into the slot, and then pull back. And it's clear.
It also does a lovely job of setting the correct height for picking up the can on the table.
Well, I was a little concerned that it may interfere with, getting there, but it I mean, that you're right. That's about the right. It's about the right height or a little bit higher for grabbing the can. The reason that it's clear is I wanted people to be able to see the electronics that are inside there. I also, part of it, put a little clear window on the top so that you can see the servo horn and the two rods that actuate the hand. So if somebody wasn't familiar with servos and said, now how do those grippers open and close? They could look through that little window there to see that.
Mm-hmm.
Now, is it true that you're basically set for automatic tool changing there? It looks like, because you just pop that right off of there. That's rack, you can have multiple tools.
So when this closes all the way, the rods line. So in theory, this could close around a tool holder, and then it could disengage from it, and this would stay on the tool holder because it doesn't take any power to maintain that grip. So yes, in theory, it could have more than one tool.
Very nice.
Yeah.
And just so you know, James, I still hope to use those absolute magnetic position sensors. They are not yet incorporated into the ARM. I had this grand plan of putting those sensors inside of the ARM and using these little belt systems that I had developed. I'm adverse to hanging things on the outside of the ARM. That said, once I started putting together the electronics for the when I started putting together the electronics that are right down inside here, I had to remove that little belt system because the board that those electronics were on was going to interfere with that belt when it did its thing. When I cut out the side panels for the ARM, you can see that there's some holes right here in the side. That's always been plan B, was to mount those sensors on the outside of the ARM, and I may have to resign myself to doing that. So I haven't given up on those absolute position sensors, but I have not yet incorporated them.
But for now, I guess red reckoning is good enough for the pop can shell.
Right. It just means that whenever, so for example, if I hit the L key for limp, the ARM, well, actually the ARM's not going to fall. This part will fall down. This part will bounce back up inside because of these springs that are on there. So that means whenever it's limp, I put it into this known configuration, something like that. I don't manhandle the rotation of the wrist because there's just too much resistance to that, even when it's limp. And then I hit a knit. I hit I for a knit, and then it enables all the stepper drivers and then assumes that it's in a certain position, and that's its starting position, other than the homing on the wrist and the homing on the just a second here. Okay, so if I go joint pivot, I think the maximum swing is 12 degrees off center. So if I go like that, oh, maximum is 11. Joint pivot 11, go. So it can go 11 degrees each direction from center. Like like the wrist, there is going to be, it's probably an hour away from being done, an optical sensor on the portion that slides back and forth to act again as a homing sensor, so that it can find that center line position. And so it'll go through, I have to put it in a known position, and then it'll go through a homing cycle on the wrist and the what I call the pivot joints, and then it's ready to go.
That's cool. That's cool.
And all of the so as I mentioned, the wrist and the rotation of the wrist and the gripper are on one wire. The sensor for the homing of the pivot is also a one wire node, and those absolute position sensors will be one wire nodes. So there's this little one wire network that goes from one end of the arm to the other.
So that keeps you cabling down to a minimum because it's all on, wait for it, one wire.
So right now I have 3 wires running from the wrist down all the way back to the controller, just 3 wires. Now, when they go through the slip ring, it's an 8-wire slip ring. So there's 2 for power, 2 for ground, and 2 for one wire. So those are redundant. And at this point, I've not had any problems with anything that I would attribute to that slip ring, any communication problems or anything.
Is that in the wrist where the gripper
Correct.
attaches? Okay.
Correct.
Well, you're a braver man than I, Greg, working with slip rings.
So it's kind of fun to do, like if I do joint, rotate, let's say 700, and then say go. So it should wind that up, right? Okay. And now
Wow.
I'm going to tell it to go back. I'm going to tell it to park. But because I don't have anything in it that says, well, 720 is just like 360 is just like 0. I haven't coded that in there yet. So it's going to unwind that 700. And again, it's a slip ring, so it's not really unwinding, but it's going to rotate through 700 degrees while at the same time moving back. But because all motion needs to end at the same time, it moves back in slow motion. So anyway, I get tickled.
This is coordinated motion. I love it. So you realize this means, Greg, that you can screw in bolts and things like that.
I can screw in light bulbs. That's right. I just need a much longer arm.
Or a really big light bulb.
A really low light fixture.
That was a bad joke. My bad.
And another robot to tell you how much better it could have done it.
Exactly. Well, three more robots that can stand around and watch.
That's pretty impressive, Greg. I really like that.
It is.
The cool thing about it too is that your hardware is not super. What's the word I'm looking for here? I mean, it's not like machined steel and like, you know, it's low cost, commonly available stuff. So it should be easy
Right.
for other people to make this arm if they want to, which I really like. And then they benefit from, you know, just being able to copy all your really extensive control stuff and the electronics and all of that without having to redesign it themselves. That's cool. I posted another little thing in the chat about Shaky, who was the Stanford robot way back when. If anybody doesn't know about Shaky, you just gotta check it out. So many cool things came out of Shaky. there's literally code running in robots on Mars that was written for Shaky back in the early 1970s. So anyway, I've loved Shaky since I was a kid. Got to see him, the actual Shaky robot, at the Computer History Museum in somewhere in the Bay Area. I can't remember. Mountain View it is. And so I decided to start putting a web page together about Shaky. So if you have anything or any links or any information about Shaky to contribute, there's a little form at the bottom of the page. You can go ahead and post it. I would love to see that.
Cool. All right. Thank you, Greg.
Yep.
Let me see here. So, did everybody get my my background this month here? Let me move out of the way so you can oh, come on. Go. I get out of the way of the right camera here. There we go. I don't know if anybody. Sometimes it feels like that. And I know if you can read you can read it all there. Math is logical, math is practical, and math is magical. So sometimes that's how it feels when you're doing engineering.
That's really nice. What is Rainbow Laboratories, and is that your company or is that a organization? Or?
I found that on I was actually found this on the web. There's actually a whole website full of these really cool backgrounds that you can use for, there's like a bunch of them. I thought, well, I'll try to remember each month to have a different background behind me. Last month you might remember was the IKEA image with 2 bottles of hydrogen and a bottle of oxygen, and then the instructions, to basically assemble it into dihydrogen oxide. So anyway, I thought I would just kind of try to find some interesting, maybe amusing, humorous kinds of backgrounds that I can use behind me.
So
I don't know.
Labs, it's very very nice, empowering queer and gender non-conforming youth, one lab at a time. That is So that's
oh boy.
Being
yeah.
That won't cause anybody any problems, I'm sure.
Okay.
At least I hope not.
Yes. Okay. Does anybody else have something that they would like to share? I don't see our presenter yet. I did shoot him an email right at the before the meeting, but I don't see him on here yet. So I do have that one of the videos there. It says make sandwiches with 3D printer. So a YouTube video. I think you posted a link to it.
Yeah, that's a fun one. I can try and share it with everybody if we're
Well,
time.
I'll tell you what. Let me see if I can do that, because I have it queued up here. So hopefully it will play. Awesome. So, okay, so I'm going to, let's see here, share. Okay, so there's that. Let me switch over here to okay, there's the video. Make it big. All right, so it's a short, it's only about 1.5 minutes, so it's a pretty short video.
So yeah, at this point, it's actually assembling the components that it just printed. So you'll notice it's like twisting them to lock them into place. I thought that was cheese at first, but it turns out that white stuff is actually bread.
Very conveniently decrusted, I might add.
Yes. Yeah. There's a certain need for consistency or regularity here.
Yes. That's pretty good. Any idea how long that actually takes? Because it looked like it was sped up.
I'm sure it takes quite a little while. Yeah,
I'm going to go ahead and play it again since it's pretty short here, because now I'm going to watch a little more carefully too what all actually happened.
Yeah, so you can see he cracks certain parts off of your bed adhesion, and then takes them and snaps them into other parts, and then rotates those parts into place, like this saw, for example. You can see get like a little catch there for different things.
Right.
There's some brilliant engineering in that in order to get that to work.
A little bit of compliance engineering.
Yes, exactly. I also enjoyed, I don't know if you noticed that, but when he deposits the bologna or ham or whatever that is onto the sandwich, he does so by shoving the ham around a bar, which is over the top of the sandwich. So in other words, he doesn't have to rotate to dump it off. He just has to shove it down between the tongs. I thought that
right.
was
Fold it. Yeah. Fold it in half.
Right.
Yep.
Fold it in half through the tongs. Now that if you go to that guy's channel, he has a few other videos where in one of them he 3D prints and then assembles a little car with rolling wheels and all of that kind of stuff. So it's one thing to 3D print a little car, and then you take it off the bed and you assemble it. But he gets the 3D printer to actually assemble the little car that he 3D prints, and it's done when you pick it up, which I thought was again pretty cool.
Yeah. Huh. Interesting.
I have been wanting to do some compliancy engineering, develop some compliant parts. I tried to set out and do that for my camera holder. I eventually gave up because I realized I didn't really have the expertise to go through and figure out how to make the joints and the levers. I'm looking for something and not finding it.
So
but
just in case anybody doesn't know, what exactly do you mean by compliance engineering?
So for example, you can make hinges that are compliant but don't have any. They have what they call flexures, so flexible parts, but they don't have any rotating parts. They don't have a hinge pin. And so I've seen some pretty amazing things that are done with those where they have a lot of control over how they move. It's not just a simple hinge. It may rotate and pivot and all these kind of complex motions, all with one 3D printed part. So I thought, I've got the camera on the top of the robot rotates through 45 degrees. And I thought, wouldn't it be cool if somehow, you know, that was all done with flexures. Originally, it was done with a hinged part with a little brass rod as a hinge pin, which worked perfectly fine, 2 parts and a hinge pin. And then it had a 3D printed gear and a smaller gear on the servo, and it all worked fine. But where the smaller gear hooked onto the servo, it stripped out. So I needed to redo that, and thought, oh, this will be a kind of a fun opportunity to do flexures. But I ended up with a cam and like a cam follower, as opposed to using gears, and I'm pretty pleased with it.
Did you manage to find it there to show us what you're talking about?
Well,
I dropped the link in there for the one that I typically fall back on when needing to explain it in the chat.
I've actually seen that video that Richard posted, and thanks for that, because that's a really cool video. It goes into some amazingly complicated and useful linkages.
Yeah, there's a newer one out there for like doing flexure compliant based like bistable switches. But
yeah, I've seen that one as well. Yeah, pop forward or pop back. Yeah, nice.
That's what I was trying to do, was trying to do something bistable so that it would, you know, kind of move and then snap to one of those 2 positions. This, if you look in the other window, you can see what I settled on. See if I can get it down there any closer.
Okay, there we go.
Okay. And if I turn the robot on, it will go through the motion. Here, just a second. Yes? No? Oh, wrong switch. I should label those switches.
A completely different robot, which is now doing something destructive.
No. So that's it uses the RC servo horn. It's got a ball bearing attached to it, and then this black bar acts as a follower, and just kind of follows that.
Is that optimized to the point where you get the maximum torque at the end points? It doesn't look like it. I was just
no
designs before.
Yeah, no, I was just trying to get that range of motion. It doesn't take a lot of torque to pivot that camera.
Right.
Anyway,
right.
That's what I ended up with.
Is that one of those 3D?
Yes, it's a RealSense 415.
I've done a little bit of work with those, and the problem that I always have is that it gives you too much information. It just floods you with data, and the processing power required to do anything useful with it is really the issue. Getting the libraries to work in a decent period of time.
Well,
have you done anything with it yet?
What I did do was I was taking the 3D data, essentially taking the point cloud and then analyzing all the points and reducing it to a grid on the ground where the value in each cell, and I think they were like 5-centimeter cells. The value in each cell, or the data in each cell, told it the average height of that cell and kind of the deviation. So if there was a lot of deviation in a cell, that meant it must be like a vertical surface, right? So then it would take that 2D grid, and for my benefit, color it, and then I could see, oh, those are walls, those are relatively flat surfaces, and then if it and of course, because it knows the average height, you might have a set of stairs which would show up as a bunch of flat surfaces, but clearly their height differs. And so it could recognize drop-offs, basically, the stairs going down. And then it would pad all of the cells that it could not travel through because they're like vertical walls or other things. It would pad them with half of the width of the robot, leaving the areas where it could travel, and then it would find a path through those areas and then just kind of wander around my house without bumping into things. And I was able to do that. My goal was 10 frames a second. And I think it was running at like 8 or 9 frames a second.
Yeah, that sounds about right compared to what I was getting. I mean, that's useful, right? Nothing wrong with that.
And that's written in Python. That's using Python, running on a Raspberry Pi 3B Plus.
Oh, I'm surprised it was that fast on a Raspberry Pi, but cool.
Yeah.
So I've got one of the little NVIDIA CUDA processors, and so I haven't done it yet, but I was going to run my video into that and do something similar to what you're talking about. But that should give me a much higher frame rate.
Video from what source?
Same kind of camera.
Okay.
The Intel Sense 415.
Yeah, very good. What I'm currently playing with is OpenCV and locating an object based on color. I'm not trying to do any machine learning object detection because I figure to find the can inside of the refrigerator, I don't really need object detection. It's a white interior. There's only going to be one can, and I get to choose the can. Now, being a root beer drinker, my plan was to use a can of root beer. Well, most cans of root beer are brown. The outside of the can is a brown color, and I could not find settings for OpenCV where it could isolate this brown color. So my fallback, not that I drank Coke, but my fallback is a can of Coke because that red just jumps. And in no time, I was able to find settings for OpenCV that could just pinpoint that red color. So that's my plan.
One of those rare cases where a marketing ideal and a robotics engineer's ideal happen to align.
They aligned, you betcha. So my plan is to locate the can based on the red, and then with the corresponding 3D data, find what is the distance to that red object, and then use that to tell the arm, okay, now go to this XYZ location and grab the can. We'll see if that all comes together, but that's the plan.
So that's probably funnier to people who have had to work with marketing people who promise something to the customer and then turn to you as an engineer and tell you to deliver it.
Yeah.
Also, is the camera going to be on the robot or on the arm?
No, the camera is on the robot. So the reason that the camera moves is because I figure when it's navigating around, I want the camera to be more or less pointing straight ahead.
Got it.
But when it comes to looking at the mini fridge, I need it to point down because we're going to be relatively close to the fridge. So that's why it moves like that.
Interesting. Yeah, that makes a lot of sense that way. So is it going to, I'm assuming that as it's navigating around it may find the can, see the can before it is within reach of the arm. So I'm assuming that there's no?
No, because it's inside of a closed refrigerator.
Oh, okay. All right. One of the best ways of not having to deal with range is to constrain the range.
Yeah, there you go.
All right. We have Professor Greenberg is online with us. And so we are going to take about a 5-minute break because I need to take a break. So whether any of the rest of you do or not, I do. So I'm going to pause recording. And if I do not restart recording, please, somebody go, whoa, whoa, so anyway, let's see. So we will be, let me see here. I'm going to jump. Oops.
Did you say that our speaker did show up or didn't show up?
Yes, he is online, and so we are going to. I'm just going to jump back to. I'm square my screen for just a moment here, and it'll take as it has been here. It's been kind of pokey getting up, but it should. You should see it there momentarily. Come on. We need a little Jeopardy music going right about now here. Come on. I don't know if it's slow upload on my end or what it is. It takes it so long. So come on. I know you can do it. Oh, I just gotta love technology, Come on. My goodness, that is really being pokey. Well, maybe I will. All right, try it again. Come on. You know you can do it.
You're burning up your 5 minutes, Steve.
I know, darn it. All right, well, let's, okay, it's just not going to cooperate. I can see that. So anyway, let us take about, so I've got, it's 12:05 my time, 11:05 your time. So let's resume here about, just turned 6. So about 11:06 or so, let's regroup. And Professor Greenberg, if you want to go ahead and share your screen, and you can just leave your title page up there. That would be great.
Sure.
So with that, I'm going to go.
This meeting is being recorded.
All right, everybody, come on back, and we will get started here. I'm very excited to have Professor Andrew Greenberg joining us this morning. He is Chief Technical Officer at the Tova Company, and he's also an adjunct instructor at Portland State University. And I believe it's at Portland State where this Cube satellite stuff is happening. So he's going to be sharing with us what that's about. And if you've looked at some of the links, it's pretty cool building these little tiny, pretty inexpensive satellites. So thank you so much for joining us this morning, Professor. And I will hand the ball over to you.
Thanks. It's just Andrew, not professor. I am a fake professor. I'm just an adjunct. So I only teach half or quarter time, I think is the right way to say it. But the fun part is I get to teach a bunch of undergraduate students, interdisciplinary undergraduate students, mechanical, electrical, computer science, to work on this big aerospace project, which I'll get into. So I was listening to the conversation earlier about OpenCV and robot arms and things. That was pretty great. So maybe I'll up the level of the technology discussion a little bit. Please feel free to interrupt. I have a 5-hour presentation that I'm gonna kind of pack into 45 minutes and try and tell you guys interesting stuff about space. You may not already know, although as amateur radio people, you know a lot. So it's kind of funny. So let's get started, and really feel free to put stuff in chat, interrupt me, whatever. I'm pretty open. So a lot of people don't think about space, and so I'd like to give a brief overview of space for just a minute, right? So you know, we're down here in the troposphere, and balloons and other things like that are like 30 kilometers, about 100,000 feet, and that's people love talking about high altitude balloons as the edge of space. That is not the edge of space, kids. That is 30 kilometers. Space is defined as 100 kilometers, which we'll get to in a second. And then all the interesting things are above about 100 kilometers for space. That's not real far, right? That's like an hour drive to space. So it's called the von Karman line because of this guy. So Theodore von Karman was a famous Caltech physicist. And interestingly enough, actually, here's a quiz, pop quiz. Does anybody know why it's 100 kilometers? What's special about 100 kilometers?
Didn't it have to do with the ability of the point at which the atmosphere no longer had a certain amount of effect on the spacecraft?
Yeah. So it turns out that if you have an airplane and you fly it at 100 kilometers, you have to fly it at orbital speeds to get enough lift to keep your aircraft up. And so it's this funny kind of thing where it's not physically possible to fly an aircraft. So that he chose that. It was like 90 something kilometers. So he chose 100 kilometers because it was close. And I thought that was adorable, which is like he was an aerodynamicist. And so that's how he chose the edge of space, which is great. So, not very far, right? Every once in a while, you should have an existential crisis about how thin our atmosphere is, because it's really, really thin. It's really terrible. In fact, going up for rockets is not the problem. It's really relatively easy to go into space. What's very, very hard is staying in orbit because, of course, we're at the bottom of a gravity well, right? And so going up is just going up the gravity well. And, a lot of people don't answer this question correctly, which is if I take a baseball and I throw it and it goes all the way up to the orbit of the moon, what happens to it? The answer is if it stops there, if that's the apogee, it falls back down. So we're at a quasi-infinite potential well, right? So the gravity doesn't go away. What we're doing is we're going around the gravity well. And just like that OMSI, or what's the Pacific Science Center? No, wait, what's the Seattle Science Museum called? Oh, well, anyway, they have those orbit tables, the big black tables with the hole in the middle, and you get the ping pong balls and they go around. It's going around, which is orbit, right? So
you were right, Pacific Science Center.
Okay, good. Thanks. Okay, so Newton had this thing, back in the 1700s where he imagined a cannon at the top of a very tall mountain, and if you fire the cannonball fast enough, it hits you in the back of the head eventually as an orbit. And that is very, very, very fast. That's 8 kilometers per second. And like I said before, it's easy to go up. It's not easy to go 8,000 meters per second. That is where 90% of your energy goes in an orbit. And why are rockets big and why are rockets hard? Because you're putting a tremendous amount of energy into a small thing. So our little satellite is 1.33 kilograms. So it's a couple of pounds, right? Maybe 3 pounds. That Coke can, essentially, in orbit, has enough kinetic energy to take out a city block, right? It's about 8 kilograms of TNT. That's how much energy you're putting in this, kinetic energy you're putting in this little teeny tiny thing. So that's why space is hard, which is interesting, not because it's up. So you guys know space, so I'll skip over this section, but just, reminding you, there's LEO, right, which is about a couple thousand kilometers. Then there's MEO, where in most satellites are in LEO. Actually, the bulk of them, I'd say about 80% are in LEO. MEO is GPS and some other comm satellites. And then, of course, you get high Earth orbit and getting out to geosynchronous at about 35,000 kilometers. So it's far away. And then, like I have to deal with a bunch of students who are snarky. And so occasionally we have to beat them into line. So as going back for a minute, so low Earth orbit takes about 90 minutes to go around the planet. And then as you go out from low Earth orbit, the orbital times take longer. So at MEO, the GPS satellites take, I think it's like 8 hours or something like that to go around the planet. And of course, you guys all know geosynchronous satellites, right? Their orbital period, they're so far away, is 24 hours. So they're going around at the same rotational rate as the planet. And so, we have this other satellite that we don't talk about a lot, which is 384,000 kilometers away. And what is its orbital period? Anybody know?
About 28 days.
Yeah, that's right. About 28 days, about a month, right? So the moon is far enough away that its orbital period is 28 days. You don't think about that as the moon orbiting, but it's the same damn thing as our satellites. It's just really, really far away, which is kind of fun. Okay, moving on. So let's take a satellite and let's break it down into parts. So we talk about a satellite bus and we talk about payload. And those words are way back in the dawn of time in the 1940s and 50s. So the bus is, of course, power system, solar cells, batteries, voltage converters, system controller, like the onboard computer, it's often called OBC, sometimes housekeeping unit, HKU, and then anything you need to run the satellite, attitude determination, orbit control, rockets, all that kind of stuff. So, and we don't usually talk about that, the bus. We usually, when you talk about, Mars Surveyor or Mars Climate Orbiter or whatever, anything you talk about the payload, what's the mission? The Webb telescope, the telescope itself is the payload. It's the thing that you pay for. And the bus, which is this box stuck underneath the big sun shields, no one talks about that. But that's kind of the exciting thing if you're kind of a space nerd, which is what is the bus and how does it work and all that kind of stuff. So we're going to talk about satellite buses mostly today, and not a lot about payloads. So let's switch gears again. Now that we've got bus and payload separated, and talk about CubeSats. So this is Bob Twiggs. Bob is from Stanford University, now at Morehead State. And he had a problem in the early 2000s, like around 2001, in which that his students that he was teaching aerospace at Stanford couldn't get satellites into orbit. It just took too long. It was too complicated. These big satellites, the size of small refrigerators, were just too complicated. So he said, what if we had a small, little, tiny form factor? And then what if we could kind of make it, a form factor that you could stack and make modular. So if you guys remember servers, internet servers or computer servers, right? They have U's or units. So 1 U is like 1.5 inches or something, 2 U's, 3 inches, that kind of thing. So CubeSats have U's as well. And each of these U's is 10 by 10 by 10 centimeters. So a 2U satellite is 10 by 20 by 10 centimeters. And then the most common of all CubeSats, the 3U, is 30 by 10 by 10. And you can do 6U and 12U, but those are not quite as common. And so you might ask, why 10 by 10 by 10 centimeters? Well, there's the obvious answer, right? Which is 10 by 10 by 10 centimeters is 1,000 cubic centimeters. That's a liter, right? No, that's not why he chose it. He chose it because he thought that the size of a Beanie Baby box was correct, and it just happened to be 10 by 10 by 10 centimeters. So the entire CubeSat form factor of thousands and thousands of people around the world, it's all based on Beanie Baby boxes, which is ridiculous. So there's a format, a standard, and the rails themselves. So the CubeSat has rails on all 4 corners. Those have to be aluminum. We'll talk a bit about that. And you've got access points. It's all very, very rigidly defined. So when you build a CubeSat, you have to build it to these specifications. So there are thousands of CubeSats now, and not just from universities, but from industry as well. So this is a 1U. You can see the solar panels, and you can see those rails I was talking about. This is a 2U. This is a 3U, and this is a 6U. Now, one of the important parts is you'll notice that this has stuff sticking out of it, and this has stuff sticking out of it. This has a monopole antenna that's not sticking out. When you fly your antenna, when you fly your CubeSat, you can't have anything sticking out. Oh, sorry, that's the wrong side. We'll get to that sticking out part in a minute. So let's get back to buses, right? So what's a CubeSat? It's a satellite, so it's got a bus and a payload, right? So it's the same thing as a giant, multi-ton communication satellite. It's just small. So we've got teeny tiny lithium-ion batteries. We've got tiny solar cells. We've got some kind of antenna that pops out, onboard computer with radios, payload, and then the payload is usually very small and not very. It's not the Webb telescope, right? In CubeSat, you've got something really small, usually a camera or comms payload or something you're testing. And surprisingly, the CubeSat form factor, that's not why CubeSats are popular. The reason why CubeSats are popular is because you take your CubeSats and you put them in a box. And it turns out the box is the most important part of the system. You take your 3U CubeSat and you put it in your 3U deployer, it's called, right? And then you take your 3U deployer and you stick it somewhere on your rocket. Doesn't matter where. And so let me ask you this question. What's the question called? I can't think of any words today. The kind of question you don't answer, right? So if you have a $500 million communication satellite on a rocket, would you allow a bunch of overstressed, underslept undergraduate students to put a satellite right next to your $500 million satellite? There's only one answer, and the answer is no. No, you would not let those undergraduates get within 100 feet or 100 meters of your satellite. And so, in fact, it turns out that the box is the most important part, because the box is an aerospace rated box that when the undergraduates put together their satellite and it catches fire and turns into shrapnel and all that, it's all inside that box. And so when the rockets go up into orbit, they let that primary payload go first, the primary mission. 45 minutes later, they open the box and the fire and the shards of CubeSat come out and nobody cares. And so that's the really interesting part. So it's a de-risking process, right? So it turns out that when you and I build satellites, the people sinking hundreds of millions of dollars need to protect themselves from whatever we do. Which is funny. And then they put the CubeSat deployers like really awful spaces, like right next to the damn engine. So we have like this incredible vibration and noise problem when we launch. But that's fine. International Space Station can deploy CubeSats. There's lots of different CubeSat deployers. And one of the really interesting things is, as this was originally meant for education, but the more and more and more people started using CubeSats, it became commercially adopted. And right now, CubeSats are by far, well, that's not true anymore. I'm sorry, Starlink is now one of the top formats for satellites. But ignoring Starlink, CubeSats are the most popular form factor. And what's really interesting is it's for the same reason, which is that even when companies build stuff, they want to be a secondary payload. They don't want to build that, they don't want to endanger a $100 million rocket or satellite. And this is one of my favorite pictures of all time. This is Planet Labs. They have a 300 CubeSat constellation in orbit that takes a picture of the same place at Earth at the same time every day. They have so many CubeSats, they can't store them anymore. And so they made little jigs so they can start piling themselves on top of each other. So this is a pile of CubeSats, a pile of satellites ready, waiting to go to orbit, which is fun. Someone asked, so the CubeSat usually deploy after the big sat is already always safe? Yes, abso-freaking-lutely. Like 45 minutes, so that there's just no possible way that the primary payload could be damaged by whatever happens when you open up the things. And you also notice that they're always pointed away from the main payload. So there's a spring that pushes out the CubeSats, and it's never pointed at the primary payload. It's always pointed away, which is funny. So some of the larger CubeSats, the 6Us, have already made interplanetary missions. So if you remember Mars Insight, the lander, they used two 6U CubeSats to relay the telemetry back from Mars, which is pretty cool. So I know that you guys are amateur radio geeks, and so I'll stop on this for a second. So look at this. This is a parabolic dish in a flat surface. So this is, I think it's an X-band, I want to say. It may be KU, but I think it's X-band transmitter receiver antenna right there. That hits this. This is a passive phased array dish, which is like the coolest thing I've ever seen. So that's pretty neat. And then and they use that from Mars, which is pretty cool. Okay, so we've gone over orbits and CubeSats and all that kind of stuff. How do you go about planning for trajectory and speed? That's an interesting question. So as a CubeSat, you don't. It turns out what happens is you get taken to orbit, and your primary launch provider, or LSP, launch services provider, puts you in an orbit. So SpaceX transporter missions will go up to 525 kilometers, and then they'll start deploying satellites. And then if you're a CubeSat, most CubeSats don't have propulsion and don't have trajectory. So they'll just go. They may be able to control their attitude, but they don't have propulsion. And so they're just in an orbit. And very slowly, and we'll talk about this in a minute, they'll spiral down and re-enter. In fact, I should have a slide for that. Take a message about that. There's a couple great slides I should put in this. So in fact, ORESAT 0, all of our ORESATs don't have propulsion. We may add propulsion one day, especially as we start to think about cislunar and other kinds of operations, but not right now. That's pretty rare. So let's talk about Portland State University. We don't have an aerospace program. We're not like you cool kids who have University of Washington. We just have a podunk little state university here in Portland. And we do have electrical, computer, and mechanical engineering. So we're this interdisciplinary student project. I'm the faculty advisor. The students do all the work, and I take all the credit from them, which is great. So what you should be having your own teams of undergraduates, really good, highly recommended. And the cool part about us is we're super open source. So everything that you're going to hear about today, that's actually published on the web. And it's open source to the point where other universities are actually using our stuff, which is great. Stanford and Cal Poly Pomona and a team in Germany, they're using our designs, which is cute. Another thing that's really important to know is that we have no idea what we're doing. This is our first space adventure, and so we don't know what we're doing. So take everything we say with a grain of salt, and know that yes, we do have one satellite up there that's in space, but in general, it's not. It's not a professional class satellite. So this is us, undergraduate students. We actually started in amateur rocketry. So we started having amateur radio payloads on amateur rockets. So we had UHF radios beaming data down. We put an S-band radio using Wi-Fi and little Linux boxes on the rockets. And we sort of looked at each other and we thought, hey, we actually built a CubeSat, but it was cylindrical in form factor, which is funny. We did the first couple of cute things with amateur rockets. We were the first to fly solid-state IMUs. We were the first to run Linux on an amateur rocket, we think. We were first to have a 3-axis cold gas jet reaction system. It's pretty great. And again, these are all the students doing this. And you can see over here, this is our first forays into roll control, where these little canard wings control the spin of the rocket. If you guys don't mind, I'm gonna put you on hold for 30 seconds. There's an alarm going off. I'm at my house, as you can see, and there's some alarm going off. I will be right back. Sorry about that.
I wonder if
these things are cool.
Yeah,
go ahead.
Really cool. I wonder if they have some sort of GPS tracking. I know typical GPS doesn't really work at elevation, especially the elevation that they're at. But I wonder how
it does. It works great.
Oh, does it? Okay.
Yeah, it's fantastic. In fact, we'll go over that. We have a GPS on board. What you're talking about is called the COCOM limits, where if you get above a certain attitude, it kills it, but not because it doesn't work. We'll talk about that actually, and interrupt me with questions when we get to the GPS subsystem. Okay, so that's the background, and there we go. Right, we built a CubeSat. So let's build a real CubeSat. So we did this really stupid thing, which is we went for back in 2016, we went for a NASA CubeSat Launch Initiative mission. We said, hey, we want to build a CubeSat, give us a free ride to space. They don't fund you, but they give you a free ride. And we thought, for sure, we'll write this application. They'll laugh at us and they'll say, come back next year after you've done more research. And we use funny phrases. We have, I hope, a sense of humor in our group. And shockingly, they let us in. And we were like, oh, God, oh, okay. I guess we'll build this thing. So that happened in 2017. Okay, so now put yourselves in. Thanks, Jen. Yeah, keeping it artisanally handcrafted, I think, is important. Now put yourself in our shoes, right? So you're about to build a satellite, a CubeSat. You've got all the standards. You've never built a CubeSat before. The right thing to do is to go buy the stuff off the shelf because you know that will work, right? So you can buy onboard computers, you can buy GPS subsystems, you can buy the solar panels. But for a 1U CubeSat, that's like 35K. Now, our students fundraise, they crowdfund, we're super broke. There's no way we can afford that. And then for a 3U, it's like 125K with attitude, determination, and control. So there's no way we can afford this. On the other hand, building your own, you guys know this, right? Building your own is fun, but it never works the first time. And there's no way in hell that an undergraduate team that's never done a CubeSat before is going to have a working CubeSat. And so, and even worse, by the time you're done prototyping it and guaranteeing it's going to work, it's going to cost way more than buying it off the shelf, right? So you can spread the cost over years, but you can't get away from the cost. So we kind of sat down and said, well, if we had the perfect system, what would it be? Well, it'd be a scalable 1 to 3U design. It would be COTS, it'd be commercial off the shelf in the sense that we would have things sitting there that we could plug in if we needed it. If you have a GPS receiver, you plug in the GPS receiver. It'd be open source because, education open source is important because if you don't know how it works, then you don't know how it works. It would be scalable with, microcontrollers and Linux boxes. It'd be really student team friendly so that we could give student teams parts of the thing. And then you'd choose standards, right, as much as you can. So we did the stupid thing and we said, yeah, let's do that. Let's literally build the system that we want so that other people can have this system when we're done with it. So this is a terrible idea. This is stupid, and you should never, ever build your own CubeSat system because it will fail. You're going to spend, tens of thousands of dollars, and it's going to be inefficient because you've got teams of students who graduate, the jerks. I mean, I try and fail the useful ones, so they have to stick around a couple more years, but they eventually get mad at you and they graduate. And then you don't have the experience that you really need in thermal and vibration and comms and stuff like that. But we did it anyway. So this is it. This is the ORESAT CubeSat bus. It is a card cage bus. You can see back here, there's this purple. All our circuit boards are purple. I'll let you know why in a second. And that's a backplane. And each of these cards has a total separate system. Now, some of you have graybeards like me, and you guys know that because Ash Park, you know that the card cages used to be cool in the 70s. And there was a reason, is because we didn't really know what we were doing. We had buses, things had to be swapped out all the time. And it's really a really good modular system for, especially an educational CubeSat. I can now give a student team an API, an application, application something interface. What's API stand for? Oh my God, I need more coffee. Programmer interface, application programmer interface.
There you go.
And so that allows them saying, you can only be this big. There's a mechanical interface, there's an electrical interface, and there's an API. So this is really good. And our little card cage system actually turns out to be better. So for those who know embedded systems, there's a form factor called PC104, which is the stacking system, often used in automotive and deeply embedded systems. We've used PC104. We hate it because you have to stack it, and if you need something out from the middle, you have to unstack it, and it's just terrible. So ours is 40% more dense than PC104 stack. There's about 8 cards, what we call them, per CubeSat unit. It's great. Really, really good. There's cons, right? It's very hard to go up and down the stack. It's not, if you build your own, individual customized bespoke satellite, then you can fit more stuff in it. But we're pretty proud of what it is. And we want it to be scalable, right? So you can actually build a 1, a 2, or a 3U CubeSat with our system. And all of this is published. We have the aluminum frames published. We have each of the subsystems are all published. So other teams and universities can grab these systems. And here's an exploded view. This is what it looks like. We have these aluminum frames that grab the cards. and we have solar panels that fit on the outside, and then the stack up all plug into the backplane. And you'll hear me here say plus X and minus X and things like that. This plus X, this part right here is on the plus X face of the CubeSat. That comes off, and when you pull that off, that's how you get access to the cards. And it's hot swappable, which is kind of nice. So I'll kind of blow over this, but the CubeSat is made out of aluminum, anodized aluminum, and it can be milled by students on a 3-axis CNC. So that's great. That's one of the things we wanted the students to be able to build it, right? It's got this really cute clamping system. One of the really, really hard parts of space is that there is no air, right? And like, who cares, right? Your stuff is going to work without air, right? But the thing that we don't think about is thermal, right? So you're using all of your power amps on your rigs are dumping watts of heat into the air. We can't do that. So we have to get the watts of heat from our power amps out into somewhere else. And the answer is into the frame. And so we have these this clamping system that when you clamp it to the outside of the vehicle with the screws, it pushes up and clamps the card. And one thing that you'll see, and I'll jump ahead for a minute, is you'll see this a lot, that there are these ground bars on the outside of our cars. And those ground bars fit right in these slots, and then we crush them. And so we have a direct, good thermal connection to ground. Not electrical, because it's anodized. It's anodized aluminum. So there's a very, very thin aluminum oxide, thing there. So that worked out really, really well. And that's right. Yeah, and the clamp transfers the heat through the ground plane. So we have to dump the PA heat into the ground plane and then get it out into the sides into the frame. And what you'll see is all of our power amps are off on the sides of the cards, right? Because we don't want them to go very far. So we do a lot of vibration testing, right? In order to get on a rocket, you have to go through a vibration test. And someone said something about that being difficult. And the answer is it is, unless you have no wires, because what's going to break when you do a vibration test? Wires and connectors. And so again, this whole card clamp system really allows you to have a really solid system. We have never had a vibration test failure, which is super cool. And that includes bumble-handed faculty advisors dropping the satellites. Yeah, I did that. Thermal, we kind of went through this. We used some thermal simulation using something called Thermal Desktop, and kind of made sure that it was going to, thermal in space is very hard. You've got minus 300 degrees off to the left. You've got 1.33 kilowatts per meter squared coming from the sun. And then you've got this big warm ball at basically 20 degrees C below you. So it's a challenging thing. Shock test. Yes, I claimed it was a shock test for the record. All right. I'll skip over this. We have these kits that you put together. So this is a 1U frame kit for one of our satellites, minus X, plus X, 2Y frames, and some of the clamps. Okay, so that was the mechanical stuff. So let's talk about the boards. So this is our backplane. We use a 50,000th inch connector, and all of our RF, because we've got radios, right? All of those are microstrips with what are called Smpm connectors. I don't remember what that stands for anymore. Something sub-miniature micro something connectors. They're pushing connectors, and what makes them really cool is they have a barrel, a built-in teeny tiny little barrel, and so when they can deal with a lot of misalignment when you push them in, which is important because we've got undergraduate, who are the worst on the satellite? Who are the people who really destroy it? It's the electrical engineers. The mechanical people are really soft and really great with it, but the EE people just destroy it. So anyway, so we've got some auxiliary buses over here. You could use an Ethernet bus if you really wanted to. We found Ethernet to be too power hungry, so we used controller area network, or CAN bus. And then it's 2022. You can get circuit boards for cheap. So the backplane is made bespoke for every single mission. We don't think that we can, produce a system that everybody will use the same. So you just make the system however you need to make it. So thank you, call out to Osh Park Circuits, who's actually based here in Portland. They do these purple circuit boards. I don't know why they chose their solder mask to be purple, but made us have a purple satellite because they give us boards, which is fantastic. So thank you to them. We use two different kinds of boards. We've got a cheap 2-layer, And then we've got a 4-layer that's RF friendly and good for high density designs like some of our Linux boxes. And then let's talk about the computing on board, right? Yeah, I never thought about that. I could blame Portland for the weird color. Thank you, James. I appreciate that. We have 3 levels of computing. We have the standard 32-bit microcontroller that used to be like the old 8-bit PICs or AVRs, right? Now they're all 32 bits. So it's the Cortex M0. It's the STM32F091, little teeny tiny 48-pin, 8x8 millimeters, and it runs the CubeOS real-time operating system. And then we use a stack called CanOpen on top of all of this, which is, if you really want to get me going on a rant, ask me about CanOpen. It's a little hard to use and may not have been the best choice, but that's what we use. Each solar panel, the battery pack, the sort of telemetry kind of systems, they all use the M0. For command and control, we use an M4F, which is the Cortex M4. It also runs CubeOS, but it's a much more complicated system. It does multi-threading and does all the things you need it to do. And it's got a floating point, which is what the F stands for. It talks to an eMMC. So for Flash, it does all the things you'd want a big control system to do. And then finally, we've got the big Moosey processors that run Linux. So if you guys know the BeagleBone series of single board computers, there's a Cortex A8 called Satara. It's a TI Satara processor. That's also integrated into this thing called an Octavo, which is a system on chip. And that's what we use. We use the Octavo system on chip on all of our boards so that we can still solder it ourselves. And this is anything that requires image processing or like serious processing, we throw a Linux box at it. And we have to have students, undergraduate students, program everything. So how do you onboard somebody? Because you've only got a couple of years to onboard somebody and then they graduate. So you've got the $11 COTS development kit. You give that to them, they blink the LED. Then you give them the $75 protocard with the holes in it so they can put their little sensor or whatever they're doing, wire it up and use that. And then by the time they've done that, they're now ready to do an actual system, right? And so this is our battery card, and you can see the processor right there. That's one of the F091s. There's the F091. So we have this kind of buildup for our students, which is really important. Same thing with the Linux boxes. This is called a Pocket Beagle, and it's $35. So we throw $35 single board computers at our CS students and say, go boot Linux and get that to work. And then when they work on the Star Tracker, it's the same damn processor right here. So it's pretty great. We've often called ORESAT a meta project in CubeSat building, a project to build CubeSats. So yeah. It is. It's a bus, right? We're creating an entire open source bus and an open source development system so that people can use the bus. So here's what that looks like. Oh, sorry. So here's the card cage, right? You can see the screws here that clamp the cards in there. And then of course you've got to program these things and debug them and do everything. And so you see these little flat flexible cable connectors here on the end of each card. These FFC connectors are our standardized debug connectors. So it's got JTAG, it's got a serial port, and then it's got a couple of GPIO that you can kind of toggle and look at and things like that. And then a common breakout board that then plugs into USB in case you don't have a USB to serial adapter, and JTAG plugs in over here. And it's a neat little system where every board uses it. And it's even got a type A for the Linux board, so you can plug a flash drive in to your Linux boards, which sometimes you really have to do. So what's the most important part of building a satellite, right? The most important part is not building the satellite. The most important part is testing. Because if you don't test the damn thing, it's not going to work because you can't fix it when it gets deployed. And so half of a CubeSat project is convincing people to put more energy into test and debug than into building the satellite. Because building the satellites, for the hardware people is fun, right? But really it's about testing, which is the critical part. So this is what we call flat sat. This is each of these boards would go into a 1U satellite. Here's the battery, here's the star tracker, here's the onboard computer. And we break out this ribbon cable for the bus. And then over here, we have the solar panels under a halogen light. And the idea is that we can run this satellite thinking it's in space and talk to it using some SDRs, and we can debug all of the different software and and get the ground systems to work and get all that stuff. So it's not only debugging, integrating the CubeSats, it's integrating the communications to the ground, which we'll get to in a second. Somebody asked, what's professionally built mean? Well, we go back and forth. We build ourselves, the undergraduate students, about 50% of the boards themselves. So we've got, a cute little reflow oven that we hack together from a toaster oven, and we do we get our stainless steel stencils from Osh Stencils, and then we've got a lot of undergraduates with a lot of tweezers, and that works really well for most of our boards. Some of our boards, especially the Octavo boards, we've built ourselves, but we have a very high failure rate because BGAs, right? So those get built professionally. We can either pay for them, which we have no money for. Screaming Circuits down here in Portland has built a lot of our boards. I should have a thank you slide for them too, but I don't right now. And so Screaming Circuits has done prototypes for the onboard controller, the OBC, and our battery packs, because those are the two critical things that have to work. Security. I'll answer that question at the end because that's a really good question. And the answer is we almost launched a satellite that you could have easily have hacked and controlled, but we didn't. Yay. While you're testing, you can't cool, like this integration test thing. This is not an environmental test. This is a software and integration test. To do an environmental test, you got to put the damn thing together and you throw it into a vacuum chamber, and then you flow liquid nitrogen through the base it's sitting on to cool it down. That's basically what you do. We're not that cool. We have some stuff, I think I'll show it later. We have a vacuum chamber, but it's kind of a crappy vacuum chamber. And you could use a vacuum pot. You don't have to use a real vacuum chamber. Space is not, especially at a couple hundred kilometers, it's not that vacuumy, which is interesting. So again, we use CanOpen. CanOpen is this ISO level 3 or 4 stack on top of controller area network. We use it and we both hate it and love it all at the same time. It's very industrial. Okay, so let's talk about the more fun stuff, especially for you guys as amateur radio. Oh, I didn't even introduce myself. KD7CJT. Sorry, I'm just technician class, but I've been amateur radio forever, and of course, with this open source bent, all of the radios we do are amateur radio. No surprise. Our club is KJ7SAT, and we've got a couple ham radios who help out, hams who help out. So this is our antenna. This is a deployable tri-band turnstile antenna. This is the UHF antenna. This is our L1. No, this is our L band, and this is our L1. L5, sorry, it's L5. So this is 436 megahertz transceiver. So we can both transmit up to it at 436.5, and the beacons it sends APRS beacons, that comes down at 436.5. So our downlink essentially is UHF. Our uplink can be 436.5, but we really like the full duplex thing. So we've got an L band uplink at 1.265 gigahertz, and that's the L band. And then finally, we've got GPS, which is L5 at 1.575 gigahertz. Now, the cute part is, remember I said, you can't have stuff sticking up inside that box, right? You have to make sure everything's in that cubic form factor, and then you deploy it. So these are literally tape measures, right, that we've cut down. And those are those white tape measures all curled up in a little spiral. And they're underneath this little door here. And this right here is fishing line. It's monofilament nylon fishing line. And this is a 3-watt power resistor. And you notice that the monofilament line goes under the 3-watt power resistor. So what happens? Yeah, we heat up the resistor, we dump the battery into it, that melts this, and then those doors pop open and the antennas pop out. So that's our deployable. And it worked great. We're really, really pleased with it. It's quasi omnidirectional as far as we know. Solar modules. We've got these really expensive gallium arsenide 30% efficient cells from Spectral Labs. If we could go back in time, we'd probably switch to silicon cells. The silicon cells have gotten really good. You can buy 25%, 24, 25% efficient cells these days. So, and for much, much cheaper than this. These are like $300 each. And there are 8 of them on our solar panels. It's the most expensive thing. We're super proud though. One of the reasons why our power system works so well is each of these panels has its own maximum power point tracker. I could take another hour and explain that, but it's really cool. The students did a stupendous job extracting the right kind of energy from it. The battery pack is a 2S lithium ion pack, and there's actually 2 of them. So there's actually 2 redundant battery packs in one battery card. It's only 7.2 volts, and it's about 5 amp hours, so it's not a lot, but it's enough to run the thing for probably 2 or 3 days if the solar power didn't get there. Didn't work. Finally, here's the really cool part. This is the UHF transceiver. So this is an AX5043 from ON Semiconductor. It's a sub-gigahertz chip. This is the, sorry, this is the receive. There's the TXRX switch. This is the receive LNA into into the chip. And then this is the power amp right there. It's just a, I believe a 1 watt amplifier. And we can do, 525 kilometers, right? Space essentially, up to about 1,000 kilometers on this using our ground station. This is the L band receive only. We have to up converter, or sorry, we have to down convert the L band. So we have a little down converter built here, and then we go back to the same AX5043 chip. And then there's the controller, and there's the local eMMC. And so far, we've only launched 1 CubeSat, which we'll get to in a second. And then we've got 2 more on the docket. This is our star tracker. It literally uses a color camera and takes pictures of stars, runs an open source star tracker program called Open Star Tracker that then can tell you which way the satellite's pointed. So right now, we're just tumbling in space, but when our next satellite will be able to control how it points, which way it points. And when it does that, we'll need to know which way we're pointed in an absolute manner. And so the star tracker's for that. And that runs CanOpenNode, and it runs Python and all the regular stuff that you'd imagine on a Linux box. So here's a GPS receiver that someone was talking about before. This is a commercial off-the-shelf GPS chip from Skytrack called a Venus. And if you ask nicely, they will give you the firmware on that works in space and works at orbital velocities. Because GPS works great in space because you don't, in fact, it works even better. You're down to like sub-meters from just the L5 signals because there's no ionospheric refraction. It's great. The problem is that there are, international traffic and arm regulations limits on GPS receivers that can do orbital velocities for obvious reasons, right? So you have to get it from a non-US source, or if you get it from US, you have to jump through the hoops of ITAR. Eventually, we want to do our own SDR GPS, and that's what this is. This is an LNA with a splitter. This is a Maxim GPS SDR chip that goes into this Octavo. That's why there's an Octavo there, is eventually we want to be doing SDR GPS. And we've done some experiments with this before, and we've gotten it to work, but it's not up to the point right now where it's really working well. So this is a future project for us, but it's flying in space right now. We just have to upload new firmware. Attitude control system. We've not flown this yet. This is vaporware. We've got prototypes, but it doesn't work. This is a really neat thing. This is called a magnetorquer. So in space, near Earth, you've got a magnetic field, right? You've got Earth's magnetic field. It extends into space. It's really weak by the time it gets out to medium Earth orbit, but in low Earth orbit, it's still pretty good. And so you can make electromagnets on your vehicle, and you can make an electromagnet and then torque against the Earth's magnetic field. And this is called a magnetorquer. And it's super cool. And so you can point your satellite, but really slowly, because there's not much force at all, as you can imagine. So to point it quickly, you need something called reaction wheels. And so we've got this thing called tetrahedral reaction wheels system, and it's got 4 wheels that spin up. And if you remember your college physics, if you spin something up in space, then everything else rotates the opposite way because of conservation of angular momentum. And so by spinning up the wheels, you can spin and point the satellite, which is pretty cool. Okay, so finally we get to the cool part from you guys, and I got to wrap it up because it's noon. So it's an amateur radio satellite. We have to talk to it using amateur radio. So we have a ground station, and we talk CCSDS, Consultative Committee on Space Data Systems, packets at 96 kilobits per second going up on L band. We we have 120 kilobits per second, sorry, going up CCSDS on L-band. And then we've got 96 kilobits per second coming down. And we call that the EDL, the engineering data link. That's when we're actually, uploading new firmware and we're downloading data and all that kind of stuff. But every 30 seconds, it does a G3RUH AXF25 packet. And in that packet is all the important health information from ORESAT. So as it goes around the planet, it's continuously pinging. Yeah, Jordan, that's another hour lecture. Sorry. But suffice it to say, you can control that by spinning up and spinning down. In fact, once you stop spinning the wheels, then you go back to your original inertial state. Because again, it's physics. You can't add or subtract angular momentum unless you have something external to torque against, which is super interesting. Go do YouTube videos on reaction wheels. They're fascinating and scary. So we don't have enough money to build a global ground station. We've got one ground station on the top of the engineering building here at Portland State. And it would be really sad if we could only, we're in our current satellite's in a polar orbit, so we'll get twice a day communication to it. But it'd be really sad if that's all we got. Luckily, there is an amazing thing, and it's called the SatNOGS, the Satellite Network Open Ground System. And it is a global network of enthusiasts. Many of them are hams in their respective countries. Many of them are not. And they build receive-only ground stations using Raspberry Pis with a rotator, DIY, UHF and L-band and VHF antennas. They point these damn things. They just let them go, and then they track satellites as they go overhead. And most amateur radio satellites use SatNOGs, and it is fantastic. It's amazing. We are best friends with, I don't have a picture with them, it's covering it up. Oh no, that's not them, sorry. With the University College Dublin, UCD. And University College Dublin is, for whatever reason, gets like the most packets from ORESAT ever, which is fantastic. And also there's this guy down here in Australia also has picked up a lot of our data. So we have a global ground station, and every day we can actually pick up data from it, which is really cool. SatNOGs, most SatNOGs physically move. They have a tracker built in, alt-az tracker. A lot of them don't. It turns out with an edge heater antenna or with a turnstile, you can actually get enough gain to talk to LEO satellites, which is pretty great. So yeah. Making things that move reliably is hard. That's really true. So, but obviously we need something to transmit. These are receive only because of regulations. So we took the SatNOGs idea and built a transmit layer on top of it. And we call this the university class open ground station. And Uniclogs is kind of a step up. So we use a Yaesu or an alpha rotator. We've got M² antennas. We've got a bunch of really good SDRs, Lime SDRs, and power amplifiers and LNAs and all that kind of stuff, and a bunch of single board computers here. And this is on the roof of the engineering building at PSU. And luckily enough, there's a bunch of universities that are now building these, which is going to be great. And so the idea is that we can coordinate these universities so that we can get more transmit and receive time on the engineering data link. This is inside the box, power amps here, L-band, UHF, and VHF PAs, pre-stages, some Raspberry Pis, antenna rotator controller, and then heliacs up to the actual antennas. That's a really good question. If we're lucky, it's 60 kilobits per second, roughly, for about 7 minutes. So I forgot what that turns out to be. It's like about a megabit or a megabyte, excuse me, that we can get, maybe 5 megabytes if we're lucky, and we have a really good pass. So it's in the megabytes per pass kind of thing, not more than that. So we have best mission patch, which is for Uniclogs. It's a unicorn with a helical antenna. Anyway, okay. Finally, let's get to answer the question: what do we have in space? Pixar didn't happen, I guess is the right way to say that. So thank you to Spaceflight, which is a Seattle company in Redmond. they gave us a free ride to space as Oregon's first satellite, which is super cool. So we built it and they flew it, and they flew it on an Astra rocket. And this is the bottom of the minus the face of the satellite. We have an S-band antenna for a S-band Wi-Fi experiment we're running on the satellite. And Oshpark and Spaceflight and Screaming Circuits and Crowd Supply, those are all companies that really supported us. It was really great. So this is the rocket we flew on. It's an Astra rocket 3.3, I think it was. And do I have a video of it? I won't really play it, but it's pretty great. This is in Alaska. So they launched it from Alaska and it goes south on the polar orbit. And for those of you who follow space, Astra had a failure right before this mission. And we were really nervous we weren't going to make it, but we did. They actually injected us into space. And then just last week, Astra had another mission that was a failure. So we threaded the needle. Oops. All right, and so this is the fun part. So where are we now? You can go to the mission dashboard and you can go to, let's go to Celestra. So where are we? We're at the South Pole right now. So we're coming over the South Pole right now. So that's us, which is pretty great. So this is everything in orbit is tracked by the 18th Operational Space Group, which is now part of Space Force. And so every day they give us updates on where our satellite is and how many Starlinks we're about to hit. There is a lot of stuff in orbit, and every couple of days we get uncomfortably close to a Starlink, but Starlinks have a propulsion, so they have to move out of the way. We don't have propulsion. So this is great. So we're headed this way. So our next pass will be over, yeah, we're not really over anything right now. But of course the Earth is rotating. And we're in a very special orbit this time around. We did not plan for it. If you look, the local star is right there. So there's the sun, and our orbit is actually right on the equator. So we actually are in the sun 100% of the time. We never go behind the Earth, which is crazy nuts. And yeah, we call it the T-shirt orbit. We've designed the thing to go behind the Earth and be in the worst case orbit and you know, like not get very much sun. It's like 20 degrees C and sunny in space for our satellite, which is fantastic. All right, so that's kind of fun to see. So this is some, excuse me, this is some of the data we got. Excuse me. Again, because everything is sunny in orbit, and we never designed it for that, our batteries are fully charged. It's kind of amazing. Like everything's fully charged. Everything's at like 19, 20 degrees C. Easiest orbit ever. In fact, it's almost a bad first orbit because we're not getting the kind of system integration and technology demonstration and heritage, flight heritage that we really want. So on our next satellite, we hope to get a worse orbit, which is funny. That's right. It is out. It doesn't even get out. It's the anti-Oregon satellite. Is the right way to say that. Okay. So what's the current status on ORESAT 0? Our ground stations are not working, and so it has gone silent because according to IARU rules, you have to stop transmitting if you don't have positive control of the satellite, and so it's not transmitting anymore, but we're fixing our ground station, and this week we hope to be able to actually transmit to the damn thing and say, hey, wake up and start transmitting again. But super proud. Everything worked. The solar panels worked, the battery pack worked, the beacons worked, all that stuff. So we're really proud of the students. And by the way, usually in these presentations, I have students do the presentation with me, but we just finished. We just had finals. So there's a big tired lump of students somewhere that are not talking, but a lot of them are amateur radio folk and all that kind of stuff. Okay, it's 12:06. I gotta keep going. our next satellite is being handed off, not in Q3, this slide is wrong, but in February of next year. This next test is a test of the attitude control system. So that's what it looks like. You can see the magnet torquers here, and you can see those reaction wheels right there, and the star tracker. So that this is a test of the attitude control system. And once we've tested that, then we finally get to that original mission that we got from the NASA. So even though NASA gave us a free ride to space, we've still not used that ride yet. We've gotten 2 other free rides to space in the meantime. And so the NASA mission is really, it's got 2 huge payloads on it. And so that's why it's taking us so long. The first is to get into the CubeSat launch initiative, you need a science mission. And so we teamed up with University College London and University of Maryland, Baltimore County to do climate science. Turns out that high altitude cirrus clouds have a huge impact on global climate models. And so nobody really knows how much of these high altitude cirrus clouds are around the globe. So we're doing a shortwave infrared camera that allows you to look at these clouds. And so that's on one end of the satellite. And on the other end of this, oh, and sorry, we did a NASA balloon mission where we tried this out, and you can see the shortwave infrared camera here. And it flew on this balloon, and we got some awesome data from it. So the second and last mission, and then I'll shut up and let you guys ask questions, is that we are doing a huge STEM outreach to the state of Oregon. So Oregon high school students are building a, hold on, I don't want to show that, are building a ground station. It's a helical antenna with a LNA that goes to a USB to Wi-Fi converter. It looks kind of like this. We did some testing of it. It's about a 12 dBi antenna for 16 turns, 12 dBi antenna. And the cool part is we will point the satellite at them with a matching helical antenna, and then turn on a camera with a Schmidt-Cassegrain telescope lens that's built into a single piece of glass. And that will give them live video from space of their position in Oregon. So this is what they'll see. This is like a cell phone in space, and this is what they'll see. And I don't know if you guys can see it on your screens, but that's their athletic field. So they'll actually have the ability to see themselves live from space. We call it the 400-kilometer selfie stick, which is adorable. And the idea is that we give the kids their own satellite for 10 minutes. And you know, you guys have space flight and Blue Origin and all this really cool aerospace stuff in Seattle and Washington. We don't have crap in Oregon. So this is our chance to kind of give aerospace to Oregon. So that's sometime in late 2023. And that's it. So one satellite in space, another test bed coming, and then an actual mission in 2023. And here's how you get in touch with us and our project. We've got a decent website that you can explore the satellite with. Everything's on GitHub, and you can always reach out and email us if you have any questions or comments or anything. And one of the things I didn't talk about is we're not just undergraduate students, we're also people from local industry. So we're always looking for what we call industry advisors, people who have technical knowledge or management knowledge who can come in and work with teams of students and help us build these things. Because, you know, we're clueless. So, oh, there you go. Do you allow non-Portland State universities to get involved in the program? Absolutely. We love non-PSU students because we don't have enough PSU students. We have people around the world that we work with. It's a little hard, but again, given the fact that we've got this card system, yeah, absolutely. We're working with like Oregon Institute of Technology. They're building their own card. We'd love other people to build cards, and we can fly it for them, or they can build their own CubeSat if they want to. So absolutely. And we meet on Zoom every Tuesday night for rockets and satellites, and every Friday at 2 p.m. for satellites. And then we have sub-team meetings, usually on Zoom too. And then if you ever come down to Portland, let me know, and we'll give you a tour of the rocket room and show you the ground station and things like that, which is kind of fun. So thank you. Sorry I took so long.
Oh, that was wonderful. This just sounds like so much fun.
It is. My day job is medical devices, and so this is my chance to have fun and be a ham and build cool stuff. So it's really fun.
Yeah. Let's see. You got a couple of looks like there's a couple of questions in the chat there. Oh, can you send me slides? Can you send me your slides?
Yeah, absolutely. If it's okay,
Okay.
I'll share a view on the Google Slides link with you.
That would be great. Thank you.
So can you do a quick overview of the orientation system? Does the mag system despin the gyros? Yes, that's exactly right. Eventually, now the interesting part is we don't really care, but if you want constant control of your satellite 100% of the time, you have to spin down your reaction wheels, because your reaction wheels will spin up and up and up and up and up as it fights drag and low Earth orbit and all that kind of stuff. And to not have them saturate at their maximum speed, you use the magnetorquers to despin them. We don't really have that problem because we don't point all the time. So we can despin the reaction in some random tumble, and we just don't care. It's fine. In fact, it's better for thermal control to be tumbling. So, and how does the helical antenna deploy? Well, do I have a video of that? No, it'd take me too long to find. Basically, it's a copper beryllium spring, and it gets pushed over a little mandrel, and then there's a top that comes down. The top is spring loaded and held down by more of that nylon wire. We burn that nylon wire, the door flips open, and the antenna just deploys out as a spring. And then we've got Kevlar line that we use to keep the spring at the helical at the right spacing. Otherwise, it would deploy too much. It's very floppy, but it doesn't matter, which is nice. Here, I can show you this, which is kind of fun. Other questions? What part of the project can an out-of-state student participate in? You know, one of the things that's really important about this project is it's just open. I think the most important kind of learning is hands-on experiential learning, not driven by some old guy with a beer. So there's anything, literally anything. We desperately need firmware people. We desperately need Linux software people. But there's anything that they want to get involved in, they can. Obviously, some of it is hard to get involved in because you have to be local to work on, debugging with an oscilloscope or do whatever. But there's a lot of ground station stuff, software to work on. There's a lot. And what I suggest people is they go read the website. They find out what's super interesting to them, and then they start showing up to some of the Zoom meetings would be the right way to do this. So this is Onshape, which is a 3D web tool, a 3D CAD tool. I just wanted to show you that. Yeah, we are not afraid to fail. That's great. Yeah, in fact, you know the phrase "fast to fail." We joke constantly that we're a little too fast to fail, but that's great. Like, so a lot of people talk about waterfall, and a lot of people talk about agile development in industry, right? And one of the most important things that I don't think that the agile people talk about is the reason agile is so important is because you fail fast, right? You fail often and you fail fast, and you're constantly correcting the requirements and constantly correcting even your customer. And that's what I teach at Portland State is that, like, let's do these spiral models, right? Where you try it first, but everything is wrong when you first try it, and then you do another spiral and you come back to it and you got less failure, and now you understand the system and everybody's on board, and that third spiral is always, like really close. So. Oh, wow. Thank you for that link. That is, I've never seen another person who called it iterative. That's cool. Neat. Thank you. So I didn't really go over this. You guys can cut me off at any time. But let me just jump back to this for just a minute because we're so proud of this. So this is not the world's smallest Schmidt-Cassegrain telescope, but close. We were looking for what are called folded optics. We just don't have the room for a telescope. And so we started poking at people around the world saying, hey, we want a Schmidt-Cassegrain telescope. Can you make us one? And this guy in the Netherlands who works at ESA on the largest telescope in the world, the ELT, the Extremely Large Telescope, also hand grinds his own lenses. And he's like, yeah, I've made this really teeny tiny telescope. Do you want to fly it? And we're like, oh my God, yes. So this is a full Schmidt-Cassegrain telescope right there. By the guy's name is Rick ter Horst. And this is the lens on a little USB camera that you can barely see. There's a bridge back there through the trees. This is what you see through the Schmidt-Cassegrain telescope. It's about 125 millimeter lens stuck in 30 millimeters. It's super cool. And there's actually a great YouTube video on this guy called Huygens Optics who talks about making it. Now, they mischaracterize us as University of Portland. We're not University of Portland, we're Portland State, but that's fine. It's still a good video. So yeah, it's 6 meters per pixel. So if you get enough students in a group, you should see them, you know, as a blob, but 6 meters per pixel is still pretty big. So you'll see playing fields and buildings and things like that, maybe a bus, and a big enough group of students, sure. So how we get a real-time picture using the helical antenna, do you depend on tumbling? So that's why we're doing this next satellite to test the ADCS, the Attitude Determination and Control System. If that doesn't work, ORESAT Live, this live video from space doesn't work. So it's critical that we have that working. And that's probably the hardest thing you can do on a satellite is do precision pointing. And so we're going to trust it, and it's going to fail in some weird way, and then we'll be ready to actually run it on the final ORESAT. We don't depend on tumbling, we depend on pointing, because we have to point that high gain antenna down at them while they point it up at us. So they've got a free cell phone app that allows them to point to a satellite given an ephemeris, orbital parameters of a satellite. And then we have their lat long. And then so we do this point and stare thing as we go overhead, because we're using Wi-Fi. We're using 802.11b in channel 3, which is 2.422 gigahertz, which is in the amateur radio spectrum. So we're power amplifying it to 3 watts. And then the about 24 dBi of gain on these 2 helicals closes the link budget, not when you're 1,000 kilometers away, but when you're about 700 or 800 kilometers away. And so we've got about 45 degrees of tracking that should close the loop when we go overhead. So
I just have to say that is freaking amazing what you guys have.
Other questions?
Really,
comments?
really amazing. Thank you for doing that.
Well, thanks for letting me talk long.
Oh yeah, thank you so much for joining us. Oh yeah, it sounds like it'd be fun to see your lab down there.
If you're ever in Portland, let me know. We definitely give tours, and it is kind of fun to see.
Yeah, okay. All right, any final questions? If not, I will let our presenter get on with his day, and thank you very much, Andrew. Appreciate it.
Yeah, thank you guys. It's always fun to spread the word and show that amateur radio is cool.
Yeah.
We like that part. And feel free to contact me offline. Let me throw my email address in here to the chat, and so people can contact me offline if they want.
Yeah. All right. Okay, thank you so much.
All right, well then I'll hop off. Thanks everyone. Bye.
Okay, bye-bye. All right, let's see here. Now I gotta get more. All right, stop.